Hello everybody, and welcome to example 4 on page 49 of the workbook. This is going to be our first example of actually calculating a matrix of a linear transformation. Okay, so let's read this example together. So they're giving us a function t from p1 of r to p1 of r, okay, and it's defined like this. T of p of x equals p of x plus 2p prime of x, where that p prime of x is the derivative. And consider the following ordered bases, beta and gamma. And then what they'd actually like us to calculate are three matrices. Okay, and we'll do these one at a time. Okay, now the first couple of calculations that we do here might seem a little confusing just because this is so new. But what you're going to see is that there's a definite step-by-step process here. And once you've done it a couple of times, you're going to get comfortable with it. All right, so let's start with the first matrix here. And again, in words, that's asking us to find the matrix of the transformation t, taking us from beta to gamma coordinates. Okay, so how does that work? All right, well, here's how we can do this step by step. Okay, so we'll start by noticing what our first basis is. That's the basis that's down here, beta. Okay, so we're interpreting that as being the basis for our inputs. All right, so the set beta looks like this 1 and x. Okay, so we're going to take those two vectors in beta and substitute into our function one at a time, t of 1 and t of x. Okay, and to calculate those, we need to go to our formula for t, which is sitting here. So t of 1 would be 1 plus 2 times the derivative of 1, but the derivative of 1 is 0, so we're going to get 1 plus 2 times 0. That's just going to give us 1. Okay, and then similarly, what about t of x? Well, we'll take x and substitute it into this formula. We're going to get x plus 2 times the derivative of x. The derivative of x is 1. Okay, so that's going to give us x plus 2. I'm going to switch the order on you and write that as 2 plus x. Okay, so far we have taken the vectors in our set beta one at a time and substituted into our function. Now, what we're going to do is to pay attention to the basis that we're going to, gamma, and asking, can we take the two outputs, 1 and 2 plus x, and write those as a linear combination of the gamma basis? Okay, well, what's the gamma basis? That's this set. Okay, so we'd like to take those two outputs and write them as a linear combination of the gamma basis. Okay, so we want to fill in those blanks. All right, so starting with the 1, okay, if we want to get this 1 here, notice that we're forced to put a 0 here. Okay, because that's the only way that we can make this x go away. And if we put a 0 there, that means we've got to put a 1 here to get a 1. Okay, so it looks like 1 and 0 are the numbers that go in the first two blanks. Okay, and then we move down to 2 plus x and ask the same question. How do we build that as a combination? Okay, well, let's see. Starting with maybe the x that we need here, the only way that we're going to get that x is if we put a 1 here. And if we put a 1 in that second blank, then that forces us to get a 1 times 1 there. And so the question is, what plus 1 would give us the 2 that we need here? We need a 1 in that first blank to do that. Okay. And so we have all the pieces that we need to write down this matrix. Okay? And so here's how the matrix works then. I'm going to see if I can sneak this in just to save some space here. So T beta gamma would be the matrix that we get. And actually, let me go to the next line. I don't want this to get too cluttered. Okay. So the matrix T taking us from beta to gamma would be, and here we refer back to to our definition, the columns need to be coordinate vectors. Okay, so the first set of coordinates would be 1 and 0. That's going to be the first column of our matrix, not row, but column. Okay, so 1 and 0. And then the second set, 1, 1, that's going to be the second column of our matrix. Okay, and there's the first of the three things that they asked us for. We just did this calculation right here. Okay, now again, kind of a lot of stuff that we did. That's going to seem a little convoluted the first time that you see it. Okay, so let's calculate the other two matrices, and you might start to see a pattern here of what's really going on. Okay, so the next matrix that we'd like to calculate is the matrix T taking us from gamma coordinates to beta coordinates. Okay, so the process is going to be the same here, just the order is different. So this time, we're going to start with the vectors in gamma, okay, and here's our gamma basis. So we're going to take t of 1 and t of 1 plus x, since those are the two vectors that are in gamma. Okay, we need to calculate those. So again, that's going to take us up to our formula. So t of 1 is going to be 1 plus 2 times the derivative of 1, which is 0. That's going to give us 1, just like it did before. Okay, and then t of 1 plus x, let's see. That's going to be 1 plus x plus 2 times the derivative of 1 plus x, but the derivative of 1 plus x is just 1. Okay, if we simplify there, we're going to get, what are we going to get? 3 plus x. So those are our two outputs, and now, sneak a peek at our second basis, we'd like to write those outputs as a linear combination of beta. Okay, and beta is this basis here. So we're asking, how do we fill in the blanks? Okay, make these outputs linear combinations of those of the basis beta. Okay, and in this case, since beta is the standard basis, not so hard to figure out what needs to be in the blanks here. We need a 1 and a 0 there, and a 3 and a 1 there. Okay, and so, same thing to get our matrix again. This time I am going to sneak it in over here. So T, the matrix of T taking us from gamma to beta, is going to have as its first column these two numbers, 1 and 0, and as its second column, these two numbers, 3 and 1. Okay, that's just the way that we define this matrix up in our definition. Okay, good. And then finally, we are down to, let's clear a little clutter away here. We'd like to calculate that matrix, T of beta. Okay, well, what does it mean if we just write beta once? Okay, well, if you look back in our definition, writing beta once just means that beta is going to be our basis for not only the domain, but also the codomain. Okay, so we'll start by substituting in the two vectors that are in beta. Again, they're 1 and x, looking up here. Turns out we've already done those calculations a couple of times. So t of 1 and t of x turned out to be 1 and 2 plus x. That hasn't changed. And because we've only got one basis, beta, that's serving as our input and our output basis, we're just going to take those two outputs and write them as linear combinations of the same basis, beta. Okay, and again, because beta is the standard basis, not too difficult to figure out what needs to go in these blanks. We need a 1 here and a 0 here, and a 2 here and a 1 there. Okay, and so our matrix for T, taking us from beta coordinates to beta coordinates, is going to be, first column is going to look like 1 and 0, and second column is going to be 2 and 1. Okay. So there's our first three examples of calculating a matrix for a linear transformation. The next video, we're going to continue a little bit with these calculations, and eventually we're going to circle back around and try to think about what this matrix is really telling us. Why do we bother doing this calculation? We're going to see that this having this matrix description is very useful to us in a number of ways.